Hey everyone, and welcome to this explainer. Now, if you're anything like me, you interact with large language models pretty much every single day. And honestly, it often feels like absolute magic. But today, we're going to look under the hood together. We're pulling back the curtain on one of the most fascinating technological leaps of our time. And we're going to discover the true, underlying engine that actually drives these systems.
You know, it's a question we all ask ourselves when an AI suddenly passes a bar exam or writes flawless Python code, or holds this deeply nuanced, empathetic conversation with us. It's incredibly tempting to believe there's a ghost in the machine, right? That the AI is actually sentient, or at least reasoning the way you and I do. But the reality is far more structured, and honestly, in a way, it's far more impressive. These seemingly magical feats, they are entirely powered by high-level geometry and statistics. Basically, it's math, not a mind.
All right, so here's our roadmap for this explainer. We'll start by looking at the illusion of intelligence, then how words actually become numbers. From there, we'll dive into the attention engine, see how these models are trained at such a massive scale, decode the probability of predicting the next word, and finally, look at how all this math is expanding beyond text into the visual world. Let's jump in.
Starting off with Section 1, the illusion of intelligence, or exactly how LLMs fake reasoning. So there's this really brilliant example from our source material about a man named Frank. The prompt given to the AI is this. Frank travels from New York City to Philadelphia by road on a Monday, leaving at 9 a.m. and arriving at noon. The next day, Tuesday, he travels from Philly back to NYC, also leaving at 9 a.m. and arriving at noon, taking the exact same route in reverse. The question is there necessarily a point on the road where he will be at the exact same time on both days? Now, the AI correctly answers yes, but when you ask it to explain its reasoning, the illusion totally shatters. A human would just say, well, imagine two people driving the route on the same day, from opposite ends. Obviously, they have to pass each other. The AI, however, it hallucinates this bizarrely complex mathematical justification using continuous functions and the intermediate value theorem. It's literally the equivalent of using advanced calculus to figure out how to cross the street. It gets the right answer, sure, but it fundamentally lacks basic human logic. It isn't reasoning, it's predicting.
Which brings us to Section 2, turning words into math, and how this translation actually happens. To understand why the AI makes those bizarre logical leaps, we have to look at its foundational trick. Because the truth is, AI does not read English.
This brilliantly illustrates how language is compressed into a format the machine can actually compute. Through a process called byte-pair encoding, the model takes all of human language and compresses it into a massive dictionary of tens of thousands of tokens. Now, a token could be a whole word, a syllable, or sometimes even just a single letter. And why does this matter? Well, because it means the AI sees language fundamentally differently than our human eyes do. To the AI, it's not reading a compelling story, it's honestly just sorting through a massive bucket of Lego bricks.
So here is the mechanical pipeline of how that translation works. First, the text gets chopped up into those Lego brick tokens. Second, each token gets assigned a simple integer label. But step three is where the real magic happens. The AI maps each token to a unique coordinate in what's called a high-dimensional Euclidean space. I know, that sounds like super heavy jargon, but just picture a vast, multi-dimensional galaxy map of concepts. Words that share meanings are plotted closer together on this map, kind of like neighboring planets. So the AI doesn't actually know what an apple is, but it knows exactly where the coordinates for the apple token sit in relation to the planets for fruit, red, and tree.
Moving right along to Section 3, the attention mechanism engine. Let's see how this builds into the core engine of the model, connecting those isolated planets of data to actually create context.
Take a look at the word bank in these two phrases. Now, to a human, the context makes the meaning completely obvious. To an AI, it's the exact same token. And this is exactly where the attention mechanism swoops in. It's an algorithm that mathematically weighs the importance of the surrounding words to derive context. When it sees bank, it actively looks at the surrounding coordinates. If it sees river nearby, the math pulls the meaning in one direction. If it sees vault, it pulls it in another. This is what allows the model to flawlessly distinguish between a muddy riverbank and a highly secure financial institution.
And what's absolutely fascinating about this fundamental rule of the attention architecture is that the AI doesn't just look at the word right next to bank. No, it analyzes the entire context window. We are talking up to thousands of tokens simultaneously. It calculates the complex mathematical relationships and interactions between literally every single word in your prompt to generate its response. All right, Section 4, training and fine-tuning. We've looked at the micro-level math,
But to make these relationships accurate, the model needs to learn from data, and not just a little data. We're talking an unbelievable scale.
15 trillion tokens. Just let that sink in for a second. For context, recent models like Llama 3 are trained on roughly 15 trillion multilingual tokens scraped straight from the internet. It is an astronomical scale of information. The model is essentially absorbing the mathematical patterns of pretty much all publicly available human text.
But as you can guess, raw internet data is pretty messy, so humans have to step in and course correct the math. First, the data gets heavily filtered to strip out the noise and harmful content. Then comes supervised pre-training, where the model learns the base patterns. After that, we use fine-tuning to make it genuinely good at specific things, like feeding it massive datasets of Python scripts so it essentially becomes an expert coder. And finally, there's a super crucial step called reinforcement learning from human feedback, or RLHF. Think of RLHF almost like giving a puppy a treat or grading a student's paper. Humans actually sit there and score the AI's answers, mathematically rewarding the model when its outputs align with human logic and preferences.
Section 5. Predicting the next word. After all of this incredible setup, how does it actually type out an answer for you?
Okay, so the crucial takeaway here is that after all this incredibly complex math, the multidimensional galaxy mapping, and the trillion token training, the AI is ultimately just calculating a probability distribution for the very next word, over and over again. And it can actually do this in a couple of ways. The first is greedy decoding, where it safely picks the number one mathematically most probable word every single time. It's predictable, sure, but it sometimes gets stuck in these weird repetitive loops. The second is stochastic generation, which introduces a temperature parameter. When you turn that temperature up, you inject randomness. The model might pick the second or even third most likely word. This roll of the dice creates variety, makes the text feel way more human, and surprisingly, it can actually help the model produce better chain-of-thought reasoning by exploring completely different semantic paths. And honestly, this is exactly why you can ask ChatGPT the exact same question twice and get two completely different answers. It's literally just rolling the dice on that probability distribution.
Section 6. Beyond Text and Multimodal AI. In our final section here, we're looking at how this exact same mathematical framework is expanding to see and hear the physical world around us.
Check this out. Notice the simulation of fluid dynamics? The swirl of colors you're seeing represents incredibly complex math, known as Navier-Stokes equations. Now, when this was fed into a multimodal LLM, the model correctly identified it as vortical structures or swirling patterns in a fluid. But how? I mean, it doesn't have eyes. It works because the model takes this image, flattens the pixels, and turns them into a mathematical sequence. It uses the exact same attention mechanism it uses for text to weigh the relationships between the visual elements, allowing the AI to mathematically predict an incredibly accurate textual description of complex fluid dynamics. No eyes required.
And that is the true mind-bending power of this architecture. Multimodal LLMs embed images, audio waveforms, and video frames into the exact same high-dimensional mathematical space as text. Whether it is a pixel on a screen, a sound wave from a song, or a letter of the alphabet, the model treats it all as just another coordinate on its vast mathematical map. It translates our physical world into a universal language of numbers.
So, we've seen today that the magic of large language models is really an illusion, a breathtakingly complex, beautifully structured illusion built entirely on geometry, probability, and immense scale. They predict, they don't deduce. But as we keep refining this math, expanding those context windows, and merging text with sight and sound, we really have to ask ourselves, if simple math can fake human reasoning this incredibly well right now, what exactly happens to our world when the architecture evolves to a point where it actually learns to reason? It's definitely a fascinating thought to chew on. Thank you so much for hanging out with me for this explainer, and keep questioning the magic.